The Royal Swedish Academy of Sciences has decided to award the 2023 Nobel Prize in Physics.
The 2023 Nobel Prize in Physiology or Medicine.
Award the 2023 Nobel Prize in Chemistry in equal shares.
The class of 2023 has been revealed. 11 new Nobel laureates are getting ready to travel to Stockholm in December to receive the most prestigious prize in the academic world.
For the discovery and synthesis of quantum dots.
In this episode, we speak to one of the new Nobel laureates in chemistry, Louis Brus, about his discovery of quantum dots, tiny nanoparticles that many of us now interact with every day. I'm Gemma Ware, and this is The Conversation Weekly, the world explained by experts. Maggie Villiger, you're the science editor at The Conversation based in Boston. Welcome to the podcast.
Thank you.
Tell us, what's it been like covering this year's Nobel Prizes?
So every year, that week in October is very exciting for the science team. When they announce the Science Nobel Prizes, we know the announcements are coming. We know the days that it's going to happen, but we have no idea who's going to win or for what research. So we can kind of guess about what work is going to be recognized, but you never really know whose year it's going to be. So the conversation has editions around the world. We try to coordinate ahead of time and kind of have a game plan in place. Additionally, our global reach means that we can easily connect via editors in different spots around the world with experts who are in different spots around the world. It's really great to be part of a whole network that can tackle these sort of Academy Awards of science that we have.
Academy Awards. I like that. In this episode, we're going to be talking actually to one of these new Nobel laureates, Professor Louis Brus, who has just won the 2023 Nobel Prize for Chemistry. Now, like in many of these awards, it's not just one person who wins. There's often two or three scientists who are recognized at the same time for their contribution to a particular field. And Professor Brus is one of these. He's one of three scientists celebrated for their work on something called quantum dots. Now, tell me honestly, Maggie, had you ever heard about quantum dots before this chemistry award was announced this year?
Well, Gemma, I can honestly tell you I had heard of quantum dots because I had edited a couple stories related to them in the past. So I knew about them, but not too much about how they work. I knew that they were in fancy QLED televisions, and I knew that they're used in medical research. I know that they're in some LED lights now too, just controlling the color of the light that's emitted. But beyond that, I do admit I didn't know how they work or really even what's so special about them besides their kind of cute name of quantum dots.
And I guess that's one of the joys of celebrating these kind of scientists who were doing their work over the last 40, 50 years. Some of them are, like Professor Brus, are kind of at the end of their careers. And we get to kind of dig down into the basic research of what they actually discovered decades later. So help us understand this and this word quantum in quantum dots, because I think it's really helpful to understand what that means.
Quantum theory basically describes very, very tiny things, pretty much on the level of atoms that can't be divided into smaller components. And the rules of quantum physics down at that very, very nano level are different from the rules of classical physics that describe the macro world that we observe and move through daily. So, for instance, quantum theory is where scientists start talking about something having the properties of a wave or a particle, depending on the circumstances that it's in. So it's sort of a weird, non-intuitive space for us. And quantum dots are super, super small nanoparticles. Down on that quantum level, their properties change based on their size. And that's pretty unusual when you're thinking in classical physics terms.
Okay. Thank you, Maggie, for giving us that understanding. With all that in mind, I called up Louis Brus, who is now an emeritus professor of chemistry at Columbia University in the US and a new Nobel laureate. Congratulations, first of all, on becoming a Nobel laureate for chemistry. And it's just been over a week now since you found out the news. Tell me, how's your last week been?
Well, it's been rather chaotic, as you might imagine. I'm trying to keep up with the email, and because I am emeritus, and because I'm ill at home, I have really no other schedule. So I'm able to sort of roughly keep up with the flow of events.
What's the most surprising thing that's happened?
Well, the most surprising thing is that I received this award at all. I certainly was not expecting it. It was last Wednesday when the phone call came. They called in the middle of the night, but my phone is set so that it does not ring at the night or to bother me. And so I didn't get the phone call, and I slept. And I only found out 6 o'clock in the morning when there was a long series of phone calls, and I returned one of the phone calls, and it was a radio station in Miami, Florida, that congratulated me. So that's how I found out.
Louis Brus was awarded the Nobel Prize for work he began back in the early 1980s when he was employed by Bell Labs, an American industrial research and innovation company. Bell Labs is famous for its scientific breakthroughs, which have won its alumni 10 Nobel Prizes. Louis was in his early 40s in the 1980s and had spent his career until that point focused on electrons, understanding what they were doing inside different types of particles. So the idea that atoms in very small particles, nanoparticles, behave differently because of their size has been around for a long time, since the 1930s. Was this something you were always aware of as you were going about your work in Bell Labs?
Oh, sure. I spent a lot of time studying molecules when I was younger. That was my basic training, was the understanding of what the electrons are doing in molecules, maybe with 10 atoms or something of that sort, chemistry. And when I was older, and especially when I was in Bell Labs, I began to study solid-state physics a little bit, to understand what electrons are doing in crystals.
So you knew that this was a possibility, but when you were working in Bell Labs in the 1980s and discovered quantum dots, it was something of an accident. Can you tell me what you were trying to do at that point, and then talk me through what actually happened?
Yeah, we knew that they existed, at least in principle. But I wasn't trying to do this, so I was working with colloidal semiconductor particles for another reason. I was studying the photochemistry that occurs on their surfaces.
Now, let's just explain a few terms here. A semiconductor is a material that conducts electricity a bit less than a piece of metal would, but more than, say, a piece of glass. A colloid is a solution of one material with particles from another material dispersed inside it. Think of a pot of red oil paint, which is a type of colloid. The particles of red pigment are dispersed throughout the oil. In his work at Bell Labs, Louis was studying colloidal solutions containing a type of semiconductor particle. He aimed lasers at the solutions to see what kind of chemical reactions would happen once the light from the lasers hit the particles.
So I was studying that using laser techniques, and I was making these measurements of the photochemistry and making colloids actually with my own hands and using recipes that were in the literature.
In glass jars, that kind of thing? Picture
just right. A little bit of this, a little bit of that, and do it exactly this way. A recipe, that's the right way to describe it. And I noticed that the property of the particle itself began to change at very small size. On the first day we made the colloid, sometimes the spectrum was different. Second and third day it was normal. And so I began to try and figure out what the heck was going on with that.
He noticed that if he left the solutions out on his lab bench for a few days, they changed colour. Gradually the small crystals were dissolving and reforming into bigger ones, in a process known in chemistry as Oswald ripening. The smaller particles appeared blue, but the bigger ones that had been growing on the bench for a few days looked red.
There certainly was a surprise when I first saw this change in the spectrum. I remember that day, basically just wondering what the heck was going on with this changed spectrum. As I say, it took some weeks to sort it through intellectually, and talking to friends who were in different areas of physics, what might be going on there. So much of what we did was, I did some theoretical work and I did spectroscopy on understanding the particles, but maybe 9 hours out of 10 were invested in working in the lab, trying to improve the synthesis, trying to get smaller particles to measure their properties.
What Louis had found was a quantum dot, a type of nanoparticle or nanocrystal that absorbs light and emits it at another wavelength. Crucially, the colour of these nanocrystals changes depending on the actual size of the particle. That's what makes them quantum dots.
So how big are we talking? How big is a quantum dot?
Okay, so they're basically maybe 10 atoms across from one side to the other.
They're absolutely tiny. Each quantum dot crystal is a few 100,000ths the width of a human hair. Or as the Nobel Prize Committee put it, a quantum dot has the same relation to the size of a soccer ball as that football has to the size of the planet Earth.
And how do you actually see them if they're so tiny, so nano?
You can't see them with an optical microscope because they're smaller than the wavelength of light. A solution of quantum dots looks like a solution of molecules. You can't see them, it's just the color of the solution changes.
While you can't see these nanocrystals with a regular microscope, there are ways to see them using other types of specialist microscopes, such as an electron microscope.
One of your fellow laureates, Alexei Ekimov, was a Russian scientist, and he'd actually observed quantum dots in coloured glass. But I understand you weren't actually aware of his findings because they'd been published in the Soviet Union.
No, that's right. The Cold War was going on very strongly at that time. He published in the Russian literature in Russian. And it was obscure journals mostly, and we did not read them in the West. And he's not allowed to travel to the West to talk about his work. I asked, among all the physicists, was there any work on small particles when I got interested in them? These ideas, I was trying to make a model of the quantum size effects and so forth, and they told me, no, nobody's really working on this. So nobody had seen his articles, basically. I found the articles, and then I wrote a letter to them in the Soviet Union. I think I sent my papers and just to say hello to them. I have a friend who told me recently that when the letter came, the KGB came to talk to the Russian scientists because they were trying to figure out why the Russian scientists had contacts wouldn't have any contact with anybody in the West. There had to be something wrong.
Wow.
But in fact, they had never talked to me or anyone in the West, when this letter arrived in the mail.
Have you met him since?
Yes. They were able to come out to the Soviet Union during Glasnost, I guess it is. And this would be the late 1980s. First, there's two of them. There's Ekimov, and then there's his theoretical collaborator, Sasha Efros, who works at the Naval Research Lab. They're able to come out. And first they had temporary positions in Germany, and then they were able to come to the U.S. And I met them. As soon as they came to the U.S., I invited them to Bell Labs. We had a long discussion.
And one of the issues with quantum dots when both you and Ekimov first observed them was how to actually produce them and keep them stable. Then in the 1990s, your fellow laureate, Mungi Bawendi, figured this out and how to easily produce them. I've wondered what you think the most striking thing that you've seen quantum dots used in is so far.
Well, it usually happens when something new is invented or a new material is invented. It takes a long time to figure out what it's really good for. Research scientists, they have ideas. Well, you might use it for this, you might use it for that. But then if you talk to people in the actual industry who deal every day with manufacturing problems, your ideas are wrong. That's not the main problem. The main problem is something else, So it's just basic research scientists are not very good at thinking about all possible applications just because they lack the experience. They kind of work in an ivory tower, if you will. So in the beginning, I'm working in the context of the electronics industry, basic research in microelectronics, and I was thinking about the particles might be themselves used in the transistor or something like that. But as I also say that, just the basic research knowledge itself was useful. First applications, people began to try and use them in biological imaging. In biological imaging, people put dyes into cells and then excite them with light or lasers, and you can get an image of the cell. Different parts of the cells have different color light coming out of that, and that helps to identify the internal structure of the cell.
There are a range of applications for this type of biological imaging. Biochemists attach quantum dots to other molecules to help map cells and organs. They've even been used to detect tumours and to help guide surgeons during operations. As scientists kept working to synthesise quantum dots, the quality and the colour of the particles kept improving.
They were emitting pure colors rather than distributions of light. So then people made the connection to the display industry. The computer displays and television displays. In a display, what you want to do is convert electricity into three colors, into red, green, and blue. You can make up any kind of image starting with just those three colors in different proportions. The people in the industry began to read about these particles, and then they made the connection that perhaps they could be used in place of the inorganic phosphors that would be being used right now. And there's a lot of credit to the Samsung Corporation in Japan. Hundreds of millions of dollars were invested in the technology of these particles to get them to the point where they could begin to manufacture displays and flat panel TVs using these particles. And displays clearly were better than what they had before.
Your work really is an example, as you've explained, about the importance of basic research, of being curious, trying to solve mysteries without a particular endpoint or industrial application in sight. What message would you have for a young chemist starting out today working on such basic research?
The world is a huge place, and you could do basic research in a huge number of different areas, So the real choice to be made is, what are you going to work on when you do basic research, If you are spectacularly successful and you discover something really interesting, that might have some application in the world, as opposed to something that you're convinced has no application. So for better or for worse, you have to make a choice in the beginning of your career or when you start research. And it's almost an inspired choice, and it takes some intuition. A good way to do it is you pick a subject that is important to technology, but there's no understanding of the science at the present time. It's a complete black box. Nobody works on it. Nobody understands basic principles. Nobody knows what's going on, but there is some evidence that something is working. So that kind of problem you can take and begin to take it apart and look to see what the basic steps are and do basic research on that.
What changes for you now that you've won the Nobel Prize?
Well, in the world, this Nobel Prize, for better or for worse, has a special meaning, in people's minds all over the world. Yesterday, the mailman came to the door, and he recognized me because my face was in the local newspaper. And he said, I've never shaken the hand of a Nobel laureate before. Shook my hand. For better or for worse, this is where I am right now. I'm sort of in a special category, whether I like it or not, and I still have my office in the university, but I don't have a research group, I'm trying to leave that to the younger people. Probably means less than it would if it was somebody 40 years old who won the prize. I'm sure it will have a bigger effect for Wendy. I received congratulations by email from a number of people who won the prize in past years and decades, and they have some recommendations, and the main recommendation is you must learn to say no. People will invite you to all kinds of crazy things, ask you to do all kinds of crazy things, and your time will be entirely taken up with making university visits, and giving little speeches. And in order to have a real life and to be productive afterwards, you have to say no to all of these extraneous invitations.
Did they have any other recommendations that stuck out to you?
To have fun in Sweden. The Swedes have an extremely elaborate schedule and of events for that week in December when the award ceremony is extremely fancy. I don't know, that's part of their culture. American culture is different. If you win a prize from the American Physical Society, it's a very low-key event, and you just show up in an auditorium and not even necessary to wear a suit, and it takes about 10 minutes to award the prize. And the Swedes are the exact opposite of this. But I will take my family, we'll take grandchildren to Sweden, and we'll try to enjoy this as a great vacation,
Well, congratulations once again. I do hope you enjoy your time in the spotlight in December in Sweden.
Quite welcome.
Thank you.
Thank you for calling.
That's it for this week's episode. Thanks to Louis Brus for speaking to us, and to Maggie Villiger from the Conversations team in Boston as well. You can find links to more of the Conversations coverage of the Nobel Prizes in our show notes, including insights into the lives of Iranian activist Narges Mohammadi, who won the Peace Prize, and Norwegian writer Jon Fosse, who is the latest Nobel laureate for literature. I really recommend taking a look. This episode of The Conversation Weekly was written and produced by me, Gemma Ware, and Katie Flood, with assistance from our producer, Mend Mariwany. I'm also the show's executive producer. Sound design was by Eloise Stevens, and our theme music is by Neeta Sarl. Stephen Kahn is our global executive editor, Alice Mason runs our social media, and Soraya Nandi does our transcripts. You can connect with us on Instagram at theconversation.com, on X, formerly known as Twitter, at TC_audio, or email us directly at podcast@theconversation.com. If you like what we do, please support our podcast and The Conversation more broadly by going to donate.theconversation.com. If you like what we do, please support our podcast and The Conversation more broadly by going to donate.theconversation.com or giving us a review or rating wherever you listen to your podcasts. It really helps. Thank you very much for listening. We'll be back next week.